Welcome to the LEAP-1B. The LEAP-1B gives its thrust to the 737 MAX family of aircraft. In this document, you'll find pilot-oriented operational explanations and tips to familiarize yourself with this new engine. We will go through the following topics: the LEAP-1B engine, engine features versus flight phases, from pre-flight phase to engine cool-down, cold weather operations. Let's begin with a short technical review. Fuel burn. The B737 MAX has been designed to reach a close to minus 15% fuel burn compared to the NG family. This target has been achieved thanks to design improvements made to the airframe, but most of it is due to a new generation of engines, the LEAP-1B family. On top of that, NOx emissions have been lowered by 50%, and the noise footprint reduced by 75%. From the outside of the aircraft, the LEAP-1B is bigger than a CFM 56-7B. The jet intake is 1.76 meters wide, which is 20 centimeters bigger than the one on the CFM 56-7B. The ground clearance is 43 centimeters, which is compliant with all the certification rules, and does not induce any limitations in bank angle for landing. Even in the case of a landing with the noise wheel retracted, the engines will not touch the ground. The improved fuel efficiency of the LEAP-1B engine is due in part to its larger fan. The LEAP's new bypass ratio is 9:1 compared to the 5:1 bypass ratio of the CFM 56-7B. The larger bypass ratio is responsible for 50% of the LEAP-1B's gain in fuel efficiency. The LEAP HPC's pressure ratio is now double that of the CFM 56-7B. It has increased from 11:1 in the -7B to 22:1 and is responsible for the other 50% gain in fuel savings. The N1 red line on the LEAP remains around 104% N1, but the actual shaft speed has changed. Red line N1 shaft speed for the LEAP is 4,586 RPM, while red line N1 shaft speed for the -7B is 5,382 RPM. In contrast, the N2 red line has been increased to 117.5%, which equates to a mechanical speed of 20,171 RPM, much higher than the 15,183 RPM of the CFM 56-7B. During high thrust operation, it is not unusual to see normal N2 indication of more than 100%. And last, the LEAP's EGT red line limit is 1,038 degrees Celsius compared to the red line limit of 950 degrees Celsius in the CFM 56-7B. Technical features. The LEAP-1B engine is made of advanced technologies and innovations. The fan is equipped with 18 woven carbon composite blades. Due to the unique 3D aero design, the blade count of the LEAP is only half that of the CFM 56-7B. While lighter and stronger than titanium blades, the carbon composite blades are also very durable relative to bird and FOD ingestion. Aft of the fan, the majority of the air flows into the secondary airflow, where approximately 80% of the engine's thrust is developed. The remainder of the air passing the fan enters the engine's core, becoming the primary airflow. Primary air flows into the three-stage low-pressure compressor, also known as the booster. Between the booster and the high-pressure compressor are the variable bleed valves, or VBVs. The VBVs are designed to avoid stall occurrences in the booster by discharging a portion of the booster's air into the secondary airflow, while the engine is operating at low RPMs or during sudden RPM changes. The VBVs open into the primary airflow and behave like scoops, catching any foreign objects that could have been ingested by the booster and evacuating them into the secondary airflow, bypassing the engine's core. After the 10-stage high-pressure compressor, primary air reaches the combustor. The newly designed combustor improves the mixture of air and fuel, providing a better combustion process compared to the CFM 56-7B. This improved fuel-air mixture contributes to the LEAP's overall fuel efficiency. Furthermore, the combustion process is lean, reducing NOx emissions from the engine. After the combustor, the hot exhaust air goes through a two-stage high-pressure turbine, or HPT. The first HPT stage is surrounded by a ceramic composite shroud, and the second HPT stage is surrounded by a cooled metallic shroud. Before leaving the engine, exhaust air passes through a 5-stage low-pressure turbine, or LPT. The LEAP 1B family of engines provides a range of thrust from 23,000 pounds to 28,000 pounds. The only difference between these engines is the delivered thrust. The hardware is the same, but the ID plug is different. The ID plug is an electronic device plugged into the engine's FADEC computer that changes the operating characteristics of the engine, resulting in changes to its maximum thrust output. Engine protections. The engine control is called FADEC for Full Authority Digital Engine Control. Beyond basic engine control, the FADEC also actively protects the aircraft. In case of an N2 engine overspeed, an electronic overspeed system, EOS, independent from the main engine calculator, will command an engine shutdown to prevent it from bursting. In case of an N1 overspeed, the main calculator will detect it and will trigger the EOS, resulting in an engine shutdown as well. Furthermore, to satisfy certification rules, the engine is equipped with a Thrust Control Malfunction Accommodation Device, known as TCMA. In case of an abnormal commanded engine deceleration, to avoid any lateral loss of control due to an excessive thrust dissymmetry, the TCMA will command an engine shutdown on the engine that is not responding normally. This device is only active during takeoff and touchdown phases when on the ground. Depending on the flight conditions, the maximum thrust made available with the thrust levers full forward will change. During the takeoff run, the maximum thrust available is full takeoff thrust. When airborne, this maximum available thrust will be maintained until the aircraft leaves the orange envelope, or 15 minutes have been spent in the orange envelope. When the aircraft reaches the green area, the maximum available thrust will be reduced to maximum continuous thrust. Within the orange envelope, 15 minutes after takeoff, the maximum available thrust will be reduced to max go-around thrust, whatever the thrust lever position. This happens in order to protect the engine from experiencing too long of high power demand.
New engine features versus flight phases. Pre-flight. On the flight deck, you will find a new engine inboard display unit, new engine start levers, new engine anti-ice panel, and new aft overhead engine panel lights. On the engine parameter display, you will find two new lights. The thrust alert light, which will light up if the thrust is different from the commanded thrust, or if the N1 goes above its amber limit. And the fuel flow alert light, in case of an abnormally high fuel flow. The engine start levers are equipped with a red light which will illuminate in the event of an engine fire or during an engine fire test. The engine panel is also equipped with new lights. The reverser command light will illuminate if the reverser lever is not down in flight. The reverser air-ground light will announce the air-ground reverser logic has failed. And the reverser limited light will illuminate in case of an inhibited or idle-limited reverser. The engine anti-ice panel is different from the one installed on the NG. All lights are amber. The engine anti-ice light will illuminate if the system is inhibited. The cowl anti-ice light will announce an overpressure condition. And the cowl valve light will illuminate when the cowl valve position disagrees with the switch position. Thus, it will momentarily illuminate when the related switch is moved, indicating a transient condition. Exterior inspection. Now, let's go through a visual tour of the LEAP 1B.
Dear flight crews, you're about to operate the LEAP 1B engine on the 737 MAX family of aircraft.
As this is a completely new motor, CFM wants to share with you some nice-to-know visual clues which will help you understand what you may encounter during the pre-flight visual inspection of your engines.
These tips are intended to increase your knowledge of engine characteristics, thereby avoiding unnecessary maintenance actions and delays.
Let's go for a short LEAP 1B visual tour, ready to fly.
In front of the engine, some details may catch your attention, especially on the front spinner, the fan blade platform edges, the fan blade tips, and the fan abradable. You may observe some paint peeling on the front spinner. The paint peeling is due to erosion or foreign object damages, also called FOD. With paint peeling on the front spinner, the engine is perfectly serviceable. You can go. On the fan blade platform edges, you may observe some irregularities. Those irregularities are due to the manufacturing process. With fan blade platform irregularities, the engine is perfectly serviceable. You can fly. You may observe some paint peeling on the fan blades, especially on the rear side of the blades. This paint peeling is due to natural erosion. With paint peeling on your fan blades, the engine is perfectly serviceable. You can go. Looking at the fan blade tips, you will notice a slight crease at the junction between the titanium leading edge and the body of the blade. This crease, more or less visible, exists on any blade and is due to the manufacturing process. The engine is perfectly serviceable. You can fly. On the fan blade tips, you may observe some white dust. This dust comes from the abradable and is due to the normal breaking in process of new production engines. With this white dust, the engine is perfectly serviceable. You can fly. You may also notice some deteriorated fan blade tips with melt resin and sometimes visible frayed carbon fibers. This deterioration is due to contacts between the fan blade tip and the surrounding abradable during the normal breaking in process of new production engines. With this kind of deterioration, the engine is perfectly serviceable. You can fly.
On the light gray color of the fan abradable, you will notice rubbing marks. The color of the rubbing varies from black to light gray. Furthermore, most of the rubbing will be located, although it may not be limited to, the 3 and 9 o'clock position. Those marks are due to the normal breaking in process of new production engines. Whatever the color of the location of the rubbing, the engine is perfectly serviceable. You can fly. Looking at the fan abradable, you may notice some cracks. As long as those cracks are axial cracks that just look like a fine axial line on the surface of the abradable, the engine is perfectly serviceable. You can go. When you have a close look at the fan abradable, you may notice some flaking in the material. This flaking, or presence of small craters, is due to the presence of little air bubbles in the material, or FOD. If the surface of the missing material is larger than 1/4 of the surface of a credit card, or if you can see the structural carbon fiber of the composite fan case, ask a technician. The technician will refer to the aircraft maintenance manual to decide if the engine is serviceable. If the surface of the crater is smaller than 1/4 of the surface of a credit card, and you do not see the structural carbon fiber of the casing, the engine is perfectly serviceable. You can go. On the fan abradable, you may notice some spots and fills. Those spots and fills are the result of a repaired crater in the abradable. With spots and fills, the engine is perfectly serviceable. You can go. Looking at the abradable just behind the fan, on the circumference, you may observe some pitting. This pitting is the result of encountering severe icing conditions. With these kinds of small impacts, the engine is perfectly serviceable. You can fly.
Looking at the engine from the rear, some details may catch your attention. Inside the center vent tube, on the low-pressure turbine blades. Inside the center vent tube, you will probably observe some coked oil, with or without the presence of liquid oil. This oil, whatever its physical appearance, is normal and comes from the engine's air pressurization internal circuits. Additionally, just after a flight, you may notice some smoke exhausting from the center vent tube. This smoke is just oil vapor. With oil vapor, liquid oil, or coked oil in the center vent tube, the engine is perfectly serviceable. You can go.
Looking at the low-pressure turbine blades, you may observe ripples along the whole length of the blades. Those ripples are due to the manufacturing process. Furthermore, you may note a discoloration of the metal, and sometimes a different color between blades. This discoloration is due to the high temperature exposition of those parts. And the color difference is explained by slightly different manufacturing processes, depending on the manufacturer of the blades. Whatever the color of the low-pressure turbine blades, the engine is perfectly serviceable. You can go. Looking at the side of the engine, some details may catch your attention, especially around the drain masts and below the drain masts. The LEAP 1B is equipped with 2 drain masts. Around those masts, you may observe some oil marks. If there is no visible oil leak, just oil marks, the engine is perfectly serviceable. You can fly. Sometimes you will notice, below the drain masts, small oil or fuel puddles. These puddles come from the different drain masts. With no visible oil or fuel leak, just a small puddle, the engine is perfectly serviceable. You can fly.
In case of an unsafe condition of the fan cowl, some warnings should catch your attention. One of the latches might not be locked. And sometimes, an abnormal spacing between the fan cowl and the rest of the nacelle may be visible. In this situation, a corrective action has to be done before you can safely fly the aircraft.
On the ground, the LEAP 1B sounds different from the CFM 56. Waiting for the aircraft reaching the apron before your flight, during the engine shutdown sequence, you may hear a pressurized air noise. This noise is due to the opening of the variable stator vanes, also called VSVs, and the closure of the variable bleed valves, known as VBVs. This noise is normal. The engine is serviceable. You can fly. In certain circumstances, for a short period of time, a grinding noise might be heard. This noise comes from the low-pressure turbine blades rubbing on their seals. The motor is perfectly serviceable. You can go.
If for any reason, with the engine spinning slowly during the walk-around, you would like to stop the fan, do not stop it by grabbing one of the fan blades. Due to the size and shape of the blades, grabbing a blade could make it twist and gouge into the fan abradable. It could also hurt you. If you want to stop the fan, it is recommended to use your hands on the front spinner to slow down the fan until it stops. Doing so, pay attention not to scratch the spinner surface by rings or wristwatches.
Dear flight crews, the engine is now yours.
Take care of it for a safe and long time on wing with no delays or cancellations.
Enjoy your new LEAP 1B.
Engine start procedure. The outstanding efficiency of the LEAP-1B is due to its technical architecture. But this architecture is subject to a bowed rotor effect on engine start when the engine is not cold. The LEAP-1B reaches cold status after a ground stop of 6 to 8 hours. Ground stops shorter than 6 to 8 hours usually result in starting engines already warm from residual heat. Short ground stops contribute to bowed rotor effect on engine start. To manage the bowed rotor effect prior to start, it is important to minimize the temperature gradient within the engine. Minimizing any temperature gradient within the engine will help maintain clearance control in rotating hardware and ensure performance retention. This is done thanks to the bowed rotor motoring logic, which is active on the ground only. During the startup sequence, the electronic engine control, EEC, will maintain N2 around 23% for 6 to 85 seconds, depending on the thermal state of the engine. The motoring message is displayed on the N2 indication during that phase. Additionally, when the engine start lever is set to the idle position, an embedded functional test is done before light off. This protocol checks the status of the thrust control malfunction accommodation, TCMA, and the electronic overspeed system, EOS. As an operational consequence, you will notice that the fuel flow indicator will read 0 for 3 to 10 seconds, with the bright blue engine valve close light illuminated. This graph represents the N2 over time during a cold engine startup sequence. After the engine start switch has been rotated to the ground position, the N2 will increase. The motoring indication will appear on the N2 gauge around 18% N2. A slight inflection will be observed around 20% N2, and the engine will then spool up again. After the motoring message has disappeared, reaching 25% or max motoring, the start lever has to be set to the idle position. At 63%, the start switch will go to the off position, and the start valve open light will go off. With a cold engine, you can expect a startup duration around 90 seconds. This graph represents the N2 over time during a hot engine startup sequence. After the engine start switch has been rotated to the ground position, the N2 will increase. The motoring indication will appear on the N2 gauge around 18% N2. The N2 will be maintained around 23% for a period of time from 6 to 85 seconds. This is the bowed rotor motoring. Then, the engine will spool up again. After the motoring message has disappeared, reaching 25% or max motoring, the start lever has to be set to the idle position. At 63%, the start switch will go to the off position, and the start valve open light will go off. With a hot engine, you can expect a startup duration between 91 and 120 seconds. Note: the extended bowed rotor motoring cycle will also occur during the first start after new engine installation, or if EEC logic is updated. During any ground start, the electronic engine control protects the hardware from anomalies such as hot start, over temperature, no light off situation 15 seconds after the start lever is moved to idle detent, and start stall. CFM recommends not to intervene during the startup sequence and let the EEC do its job. If an aborted start is necessary, the EEC will automatically abort the start by turning off fuel and ignition. Allowing the EEC to abort the start instead of manually aborting the start will allow the full benefit of the EEC adaptive start capabilities during the next ground start. After an automatic start abort, the EEC will keep the engine motoring and will adjust the fuel flow schedule for next startup attempt. The flight crew will have to set the engine start lever to the cutoff position once the EEC has aborted the sequence. During the start sequence, it is not unusual to see EGT levels very near the start EGT limit. The rate of EGT increase is typically low when approaching the start EGT limit. Be patient. The EEC will manage that situation without any pilot intervention. Furthermore, the LEAP-1B usually has two subtle EGT and N2 rollbacks, or slower rate of increase. The first typically occurs after starter cutout. The second rollback occurs just prior to the engine reaching stable idle. The EGT and N2 rollbacks are not a sign that the startup sequence is complete, and no bleed configuration changes or generator selections should be accomplished until the start EG tick mark disappears from the EGT indication. The disappearance of the start EGT limit is the indication that the start process is complete. Let's now have a look at cold and hot engine startup sequences.
LEAP-1B startup sequence. Cold engine. Engine start switch rotated to the ground position. EEC powered. Start valves open and red tick mark appears on the EGT gauge. Remaining EGT shows the engine is cold. 18% N2, motoring indication displayed. N2 keeps spooling up. 25% N2, start lever moved to the idle detent. Fuel flow at 0 for a few seconds. Fuel flow increases and light off. The EGT peaks can go very close to the EGT red line. First EGT peak. Second EGT peak. 63% N2, start switch rotates to the off position. Starter cutout. It is not unusual to see another EGT peak after starter cutout. EGT red tick mark disappears, indicating the end of the startup sequence.
Hot engine. Engine start switch rotated to the ground position. EEC powered. Start valve opens and red tick mark appears on the EGT gauge. Remaining EGT shows the engine is hot. 18% N2, motoring indication displayed. N2 stabilizes around 23% and the motoring indication remains visible. Motoring disappears and N2 spools up again. 25% N2, start lever moved to the idle detent. Fuel flow at 0 for a few seconds. Fuel flow increases and light off. (63% N2), start switch rotates to the off position. EGT peak. The EGT peaks can go very close to the EGT red line. EGT red tick mark disappears, indicating the end of the startup sequence. Taxi. The LEAP 1B keep-out zone is larger than the CFM 56 zone. Keep this in mind when you are beginning to taxi or approaching the apron for the safety of ground personnel. Engine warm-up. Before applying takeoff thrust, there are two very important points to check. Look for an increase in oil temperature. Make sure the engine has 3 minutes of warm-up. The minimum oil temperature prior to setting takeoff thrust is 31 degrees Celsius. For cold-soaked engines, extending the engine warm-up time to 5 minutes is beneficial to slightly lower EGT during high-thrust takeoffs. This is often beneficial at higher altitude airports, where higher thrust levels are typically required. Takeoff. Let's have a look at the thrust reduction methods. Today, with this current temperature and using max takeoff thrust, you could take off at max takeoff weight. But today, your current takeoff weight is lighter than the max takeoff weight. Thus, what lower thrust level would be sufficient thrust to use for takeoff at this takeoff weight? It is the thrust the engine would produce if the current outside air temperature was the assumed temperature. This target thrust is computed with the current conditions of the day, leading to a reduced takeoff N1 and a reduced takeoff EGT. Refer to the FMC options for the maximum possible thrust reduction using the assumed temperature method. The other way of reducing the takeoff thrust is to use a fixed D rate. The fixed D rate levels correspond with the D rate options selected from the FMC. The fixed D rate option limits the takeoff thrust to the selected fixed D rate, which is the basis for takeoff performance calculations. It is possible to apply the assumed temperature method with a fixed D rate thrust. In this case, the computation lines of the derated engine are starting at lower levels. Once the fixed D rate has been chosen, the assumed temperature method is applied. As the baselines are lower, the new assumed temperature might be lower, but the overall thrust reduction can be equal or greater than using the assumed temperature method alone. Refer to your FCOM for maximum thrust reduction authorized. Climb. The FMC will automatically calculate the best climb thrust based on the takeoff thrust level. CFM recommends using the automatically armed climb thrust instead of manually selecting a higher climb thrust to minimize overall engine deterioration. Cruise. In cruise, you will notice that the LEAP 1B fuel flow is much lower than the CFM 56 one. Sometimes, you will even read values lower than 1 ton per hour. In flight, in case of an engine flameout, the EEC will activate the auto relight feature. If you need to manually restart one engine, be aware that in contrast to what is done on the ground, the EEC will never shut down the engine in case of hot start or overtemp situation. Nevertheless, CFM recommends you let the EEC do its job. If a hot start situation is detected in flight, the white flashing box will appear, and the EEC will interrupt fuel and ignition for 1.2 seconds to avoid reaching the EGT red line. However, the start process will continue. You'll need to abort the start sequence in flight only in the case of an overtemp situation, indicated with the red box. Furthermore, if a start stall is detected, the EEC will interrupt fuel and ignition for 1.2 seconds, then continue with the start process. The flight crew has nothing to do, just monitor the EGT red line. If you need to perform a windmill start, carefully read the non-normal checklist. You will see that there is an additional step asking to switch off the engine hydraulic pump on the affected engine. This is important because engine-driven pump drag greatly influences the windmilling speed of the engine. Descent. Depending on the flap's position and the engine anti-ice status, the flight idle thrust changes. This table comes from the FCOM. Just be aware that icing idle is higher than approach idle, which is itself higher than flight idle. Landing. Thanks to its higher bypass ratio, the LEAP 1B thrust reverser is very effective. CFM recommends coming out of max reverse by 70 knots to minimize the potential for reverse gas flow and FOD ingestion. Engine cooldown. The cooldown period can begin when the aircraft is on the ground at idle thrust. Thus, if an idle reverse landing is performed, the cooldown time begins at touchdown. If reverse thrust higher than idle is used, the cooldown time starts when the engines are returned to idle thrust. The minimum required cooldown time is 3 minutes and must be followed to minimize the potential for oil and fuel coking effects. Those fluids will bake into coke when in contact with hot parts.
Cold weather operations. Here are the different parts subject to icing in the LEAP 1B. The engine air inlet, the front spinner, the fan blades, and the booster splitter. For the air inlet, use the engine anti-ice switches. Note that all lights are now amber. For the front spinner and the fan blades, use the fan ice removal procedure when flying in moderate to severe icing conditions. It is the only way to be protected from ice accumulation on the spinner and the fan blades. As for the booster splitter, it is automatically de-iced. The EEC controls this feature, which is activated at low RPM. There is no cockpit indication of the system activation. The booster splitter can be subject to ice accretion. To de-ice this area, hot air is injected in the splitter and blown onto the blades of the first stator stage. The LEAP 1B can also defend the engine's core from ice crystal icing conditions. To prevent ice accumulation in the core, the EEC will command an opening and closure cycle of the variable bleed valves. This is automatic, and there is no cockpit indication. A slight change in EGT might be observable. Nevertheless, if ice crystal icing is suspected, CFM recommends to leave the area, as you would do with a CFM 56-7B. For taxiing in icing conditions, refer to your FCOM. The LEAP 1B ice shed procedures are required when operating in ground icing conditions. Thank you.